title of the conference seriously about Lie theory without groups. Okay, so we'll be doing a comparison between, well, lies at the core of local geometric Langlands quantum duality. So it compares an object for G and an object for the Langlands dual of G, but the comparison passes through something that really has no Lie group inside. It passes through something combinatorial. So, kind of, and for me, this line of reasoning is, well, I find it interesting that you can really recover a group theoretic object from combinatorial data, but not by generators and relations, but, well, by some, well, categorical procedure. So I should state that this started off 10 years ago as a joint work with Jacob Lurie. Then we abandoned it for a number of years, and then I recently restarted again with Lysenko with a different approach and different proof. All right, so what we'll be doing, we'll compare, write the symbols. It's Whittaker category for the group G, twisted by Q, and so it will be proposed equivalence. Let me designate it as a conjecture with the representation of Lustig's quantum group at the same parameter Q, but for the Langlands dual. Okay, so first let me say what Q is, but maybe, so even before this Q, so these are sheaves on something, and so I have to specify sheaf theory. So this sheaf theory can be really anything, but in order for the comparison to hold as is, the sheaf theory needs to be Betti. So just constructible sheaves in classical topology, modular minor glitch, which I'll comment about. However, as the talk proceeds, it's just the quantum group only makes sense that the quantum group is a Betti object. But as the talk proceeds, we'll write a different presentation of this category that makes sense in any sheaf theory. So you start a sheaf theory, and now I have to tell you what Q is. So what Q is a parameter for a Kummer local system. So Kummer local system is, imagine GM, and just write a multiplicative local system on it. So for example, if your sheaf theory is étale sheaves over some ground field K, and let me denote, well, by E, the field of coefficients, Q will be a homomorphism from, let's say, nth root of unity to E star. So when Sheaves in classical topology, so this Q is an element of the field of coefficients. And when sheaf theory is D-modules, this Q is an element, so D-modules over some ground field K, so it will be an element of K mod Z. So these are parameters for the Kummer local system. So let me tell you how this thing enters. So in general, if you have some base Y and you have a line bundle L and Y, you can, and a parameter Q, you can create a twisting on Y. So there's this notion of twisted sheaves on Y by means of L and Q. Let me denote this category by, I use the shorthand sheaves Q and Y. And what I mean is the following. You consider, so let me denote by Y tilde the total space of this line bundle with zero section removed. This is a GM torsor. So these are sheaves on the total space of Y tilde, which are monodromic with respect to, well, they're equivariant with respect to GM against this character sheaf, against this Kummer local system. equivariant with respect to GM against well, let me say the Q. Is that clear? Is that okay? All right.
What is n? You have mu n up here.
Well, it's a
For each n you have it.
no. The n, view them as a projective system for some n.
Ah, I see.
If you think in terms of 3, well, in terms of 2, it'll be, well, it's a torsion element. But all right. So now I'll introduce the left-hand side, this Whittaker Sheaves. So we first consider sheaves, and again, so it's in any of our sheaf theories. So let me say that when I write sheaves, I always mean the derived category. That's my shorthand notation. So I consider sheaf Q on the affine-Grassmannian. And so this affine-Grassmannian comes with a kind of canonical line bundle. And so that's why this makes sense. So use on the Grassmannian. So one should be careful here that so the affine-Grassmannian is acted on by the loop group of G, and this line bundle is not equivariant with respect to the loop group. Namely, it's equivariant, well, with respect to the central extension, well, the Kac-Moody central extension of the loop group. But we'll be using equivariance against loop group of N, and this extension automatically splits over N. So it makes sense to impose equivariance condition against the unipotent group, even on twisted sheaves. So the definition of the Whittaker category, well, it's this. You consider this category of sheaves twisted, and you impose equivariance condition with respect to loops, loop group of N, against a non-degenerate character. So let me just say what I mean by non-degenerate character. So N maps to the Gaussian modulo of the commutant, which is the product of copies of the additive group according to the vertices of the Dynkin diagram. So the non-degenerate character, you factor through this projection. So you go to the GA of K, and here, well, so let's not worry about it too much. So you don't have a canonical character from Laurent series to the ground field. You would have if it were not Laurent series, but one forms with values in the Laurent series. In this case, you have a canonical residue. But just to simplify the discussion, let's assume that we locally chose a local coordinate, so they have this residue. So you take the residue along each vertex of the Dynkin diagram and take the sum. So this is so this gives, this is what I call non-degenerate character. So let me call it GA. And so when I write this, so in general, if you have, okay, so now on GA, there is the canonical character sheaf, namely the Artin-Schreier sheaf. You can pull it back with respect to n of k, and you get a character sheaf on n of k, and therefore, well, if n of k was not this huge object, if it were just an algebraic group, it would make sense to talk about equivariance condition on sheaves against a character sheaf. So in general, if you have, say, chi is a character sheaf on some group H, by which I mean it's a local system which behaves multiplicatively. So this multiplication map, and with multiplicative behavior, I mean that if you pull it back, this local system, you get the external tensor product of it with itself. If you have such a thing, and if H acts on some variety Y, then it... Ah, you mean line?
Yeah.
This good or?
No, this top one.
So this,
Yeah, this one.
and yeah. So if H acts on Y, it makes sense to talk about Sheaves equivariant for H against the character chi. And what I mean by this is that, so H acts on Y, and you think about Sheaves on Y, we call this action map. So with the property that if you pull back your sheaf with respect to the section map, what you get is the character sheaf along the H variable and your F along the Y variable with all the compatibilities. This must behave. Well, if H is unipotent, it's a property, but in general, it's a datum. All right. So I have to say a few words what I mean by this when N is a loop group, but in fact, so it's automatic. Basically, it is as is. So specifically, so this N of K, it's not only a group in scheme, it's actually int group scheme. It's a union, it's a rising union of group subschemes. So let me write it as a union of some N alpha. And all of these guys are pro-unipotent. So, so when I put an equivariance condition, N of K chi, it'll be the intersection, again, intersection because this equivariance condition for unipotent group is really conditioned. It defines a full subcategory over all alpha of the corresponding subcategories for these N alphas. And, well, let me just say what you do for each particular N alpha. Well, the affine Grassmannian itself can be written as it's an in scheme. It can be union. So let me fix an index alpha. It's a union of subschemes, finite dimensional, such that each is stable with respect to your given N alpha. And so when we pose so this is the inverse limit with respect to restrictions of sheaves on each of these guys. And now we are essentially in a finite dimensional situation because the action of each N alpha on yi factors through a finite dimensional quotient with a pro-unipotent kernel, well, with respect to quotient by a pro-unipotent subgroup. And for the purposes of equivariance, this pro-unipotent group can be ignored. So it's just equivariance with respect to the quotient which effectively acts. So let me say just one word how this thing, so this gives a formal definition, and you might think that this is unmanageable because we're dealing with this infinite dimensional objects. So let me give an example how this thing looks like. So let's just strip all the decorations. Suppose you have a group in scheme which is just an A infinity, which, you know, it's a union of ANs as additive groups, one embedded into the other. It's in the version of A infinity. So, and let's view it as acting on itself. And let's even ignore the character. Let's understand how this category looks like. We're taking equivariant sheaves, sheaves on the group, equivariant with respect to the action on itself. Well, you expect that to be the category of vector spaces, and indeed it is. But under this equivalence, so the generator, so again, I denote my field of coefficients of my sheaves by E. It corresponds to the dualizing sheaf. So again, the dualizing sheaf, so by definition, the category of sheaves on in scheme is the limit of categories on schemes that comprise it. So it's an object of this category is a compatible system of sheaves on subschemes that comprise an in-scheme compatible under restrictions. And when I say dualizing sheaf, it's a system of dualizing sheaves on each, which indeed shriek restrict to each other. So the point to notice here is that on any in-scheme, the category of sheaves has a T-structure, but this T-structure is not separated. There are objects that are all of whose cohomologies are 0, but the object itself is non-zero, and omega is one of them. So it lives in cohomologically in minus infinity, but it's not a non-zero object. So the point is that this equivariant, this entire equivariant category consists of objects that are invisible from the point of view of the T-structure. And this is one of the reasons that, so none of this was done 20 years ago because people were afraid of manipulating objects in the derived category that are invisible from the point of view of the abelian category. So it's this something that really lives in the derived category. Modulo. Yeah, so I will do it. But I'm saying this from the point of view of the original T-structure, this object are nil. Sacha. Yes. So yeah, when I set up sheaves, I'm by definition a sheaf on blah is a limit of sheaves on finite type schemes, but limit of all with respect to shriek restrictions. All right. So now let me say a few words about the structure of this Whittaker category. So the Fine-Grassmannian is a union of orbits of the group n of k. So let me denote these guys by s lambda. So s lambda is, oops, it's my line, is n of k times, let me call the point t to the lambda. And we can, maybe just do it here. Is it okay? No, yes. So we can study the corresponding category on each orbit separately. And in this case, we basically are, in this example, modulo one caveat that we have this non-trivial character. And what you see is this, that this will be vect if lambda is dominant. So lambdas are co-weights, and it's 0 if lambda is non-dominant. Well, which is kind of what you expect. If you want it to match the quantum group, so the irreducibles are parameterized by dominant highest weights. So, okay, so now let me denote by I lambda the embedding of this orbit, and there are the corresponding functors. So, So there's a tautologically defined functor, which is I lambda upper shriek. So it happens to have a left adjoint I lambda lower shriek, and there is also I lambda lower star. And well, these two functors, well, again, this category is either vect or 0, provide you what you may call standard and co-standard objects. So you denote, say, delta lambda, the I lambda lower chic of the dualizing. Well, again, up to this character, and nabla will be lower star, and in this way you get highest weight category. So and as just Roma remarked, with its own T structure. its highest weight in the derived sense, but it has a T structure. So it has its own T structure, which has nothing to do whatsoever with the original T structure on the affine Grassmannian, if you forget. All right, so this is the structure of.
In this structure, will then end up like
Oh, it will. The equivalence of the road will be T exact with the quantum group. All right, so. So I should say that, well, I did this for the affine Grassmannian at one point. So at one point, I think, so I'm thinking of x as a point on the curve, and what I was denoted k is the local field at this point, and O is the local ring. So all of this can and should be done factorizably. So maybe I'll need it for the sequel. Let me just say a brief word.
But this Q is really like a quadratic form.
So I don't want to go. So because time is short, I made Q a scalar. But so as many of you have seen, there exists a version of the affine Grassmannian over nth power of the curve, and basically everything factorizes, and you can, in the same vein, introduce the Whittaker category on the affine Grassmannian of n for any n, and so there's a factorization structure. And the equivalence that I wrote before with the quantum group, it's an equivalence of factorization categories. So I'll come to that in a little bit. All right. Okay, so now, I've defined the left-hand side, the Whittaker category. Now I have to talk about the quantum group. So in here, so I really will have to introduce some tools from higher algebra. So rep Q G starts off as a braided monoidal category with ribbon structure.
So when you say that, what kind of representation?
Well, first of all, it's Lustig's quantum group.
Yeah.
So by definition, it's the incompletion of the category of finite dimensional representations. Yeah. Of algebraic representations. Yeah. With ribbon structure. So let me make a conceptual leap and just say that whenever you have a braided monoidal category ribbon structure, you can attach to it what you can call a factorization category on any curve. So this is carried out in detail in Lurie's book. So namely, it's a sequence of categories over x to the n, any curve, and with some factorization structure. And if you wish, the category attached to a point is the original rep QG. And so the braided monoidal structure, well, it's exactly the structure that allows you to, well, basically fuse points.
But curve is just
Any.
surface, topological surface.
This is completely topological, so this is just an oriented surface. So such that for n equals 1, the fiber over a given point x is the original rep QG. So now I want to do a particular example of this that everything will rely on. So namely,
What about here? Here X is algebraic or topological?
so here it's algebraic. So let's consider the case when G is a torus. And I wrote this equivalence we want to prove, and let's see what it means for the case of the torus. So namely, we consider the factorization category attached to rep Qt, and well, x to the n. And I want to say that in this case, the equivalence that we want to prove, so what is it? First of all, in this case, there is no Whittaker condition. We are really talking about just sheaves on the Fine-Grassmannian, but twisted by my Q. So it will be sheaves on the Fine-Grassmannian and so it's basically, it's some kind of tautology, if you think of it. So for example, if you think of what's happening at a point, so rep Qt as a category is just the same as rep T, so but it check. Because we are doing this for the quantum group. So this is just vector space is graded by the weight lattice for T check, which is the same as co-weight lattice for T, and the Fine-Grassmannian, it also looks like it's just discrete in this case, and it's just co-weight lattice for T. So this category is the match, and what you have to see is that, and at a point this twisting plays no role. However, so in this statement what you have to see is that when you start moving the points around, this twisting that introduced by Q exactly matches the non-trivial braided structure on this category introduced by, well, by this Q. So this is kind of the point of departure. All right. So
So you should have to identify both things in this case. A braided category, you have to prove it.
well, this really lives as a factorization category. I rather transform this braided monoidal category to factorization and do something very explicit. All right. So what I'll do now, I'll transform, but just also notice that so far this only makes sense in the Betti setting, where this makes sense in arbitrary sheaf theory. So when I said that I'll write versions of the quantum group that make sense in an arbitrary sheaf theoretic setting, I'll basically express the quantum group in factorization terms, and these terms will also already make sense in arbitrary sheaf theory on the right hand side. All right. So the next step is really to express the original category rep Qg in terms of the factorization category rep Qt. So let me just to simplify things, I'll be dealing with the rep Qg at one point, but in order to do this, I'll have to consider the factorization structure on rep Qt. So even though I'm not trying to make rep Qg factorize, I will have to make rep Qt factorize. All right. So so I'll need to also recall a general construction from Lurie's book. So if you have a braided monoidal category, you can talk about what's called E2 algebras in it. So in the monoidal category, talk about E1 algebras. In the braided monoidal category, talk about E2 algebras. And moreover, if you have, so B E2 algebra in a braided monoidal category, we said that to a braided monoidal category you can attach a factorization category, and to a B you can attach a factorization algebra inside this factorization category. All right. So
this is like a commutative version of commutative algebra, right?
Well, it's not commutative because you cannot talk about commutative because rep Qt is not commutative. It's only braided.
Well, you can talk about braided commutative algebra in braided category.
Well,
in the usual sense. And this is a homotopy.
but again, it's not a full commutativity. If Q was equal to 1, if rep Q was just rep T, if it were just a symmetric monoidal category, E2 algebras is not the same as commutative algebras. All right.
The weakest possible notion.
Well, weakest in the hierarchy. So there's E2, E3, and so on. E infinity is commutative. Okay. So, and then I'll have to perform one more step. So if you have a monoidal category, if you have an augmented associative algebra, so it's just associative algebra, well, you can create from it, by the procedure of Koszul duality, another associative algebra by taking x from the augmentation to itself. So it gives rise to a B, which is x of A from K to K. And this is another associative algebra. In your monoidal category. So now, if you live in a braided monoidal category, it makes sense to talk about Hopf algebras. And what Hopf algebra is, if it's you can think of it as a co-algebra in the world of associative. It's a co-associative algebra in the world of associative algebras. And note that this assignment is contravariant. So if A was a Hopf algebra inside your braided monoidal category. So let me denote it by, well, B is the Koszul dual. Then this B, which was defined as the Koszul dual of A, will be an associative algebra in the world of associative algebras, which is by definition an E2 algebra. From which, and you manufacture this factorization gadget. And so we denote this composite procedure. So A goes to, by means of Koszul duality, to B, and that goes by means of this factorization. Let me use a shorthand notation. A goes to omega. So that is to say, if you start with a Hopf algebra in RepQT, you can manufacture from it a factorization algebra in RepQT that I call omega of A. It's a construction that we will be using all the time. So specifically, we'll consider the following three examples of A's. So one A will be Lustig's quantum n+, which is indeed a Hopf algebra in RepQT. Another example will be the Gaitsgory version of Euclid n+, and the third example will be the small quantum group version. And we'll manufacture from each three the corresponding factorization algebra, and I'll denote them omega q Lustig, omega q Gaitsgory, and omega q small. And all are factorization algebras. In RepQT. All right, so, and it's using these algebras that will reinterpret the category of representations of the quantum group. So let me say a few words how it's done. So this is done as follows. So this procedure of Koszul duality can be applied not only to algebras, but to modules over algebras. So you can consider the functor, the category of just left A modules. So A was augmented algebra, so it makes sense to consider A modules that are local and nilpotent. And causality defines an equivalence between this category and the category of B modules. So namely, M goes to X over A from the augmentation to M. Okay, so, and moreover, this functor, so note that A was a Hopf algebra, so this is a monoidal category, and B was an E2 algebra, so left modules for an E2 algebra are also monoidal category, and this functor is monoidal. So we have this monoidal equivalence. No, it's nilpotent A modules with all B modules. It's exactly like this. So I'm working with large categories. So compact objects here go to perfect objects here, but then I take incompletions. So now, so this is a monoidal category, and moreover, it's a monoidal category over the braided monoidal category rep QG. So it makes sense to talk about Drinfeld centers. So we take the Drinfeld center of this monoidal category, but relative to the existing one, namely rep QT of A mod nilp. And, well, again, it's a general feature of this theory that under this equivalence, so this equivalence will give rise to an equivalence between this and what you can call omega A factorization modules at a point. So that's kind of the main input from, so if you consider B modules, left B modules, if you consider its center, it has a very nice interpretation in terms of its factorization picture. This is indeed factorization modules. So basically, kind of this kind of equivalence was at the core of Bezrukavnikov, Finkelberg, Shechtman book. So that's basically their book, which was written 25 years preceding the development of this theory, was constructed such an equivalence in a hands-on way.
So you're saying that omega A should be defined in such a way that we have this equivalence?
Well, omega A was defined, right? It's causal dual of, well, it's a factorization algebra corresponding to E2 algebra B, and B was the causal dual of A. So now this is something that we understand pretty well. So what are these? These are modules. So if you have a Hopf algebra, we know how to think about the Drinfeld center of its left modules. So these are, pardon me? So it's it's Drinfeld center of this category. It's not deram. It's other der. It's not even doctor, no.
And KD is both causal dual and cut de Concini.
Yes, this is unfortunate.
But you can write de Concini cut.
Let's go on.
Right. So what are these guys? So you can think of them as follows. So these are, well, these are objects in rep Q of T that are endowed with the local nilpotent action of M. And then to upgrade it to the structure of object with Drinfeld center, you define an arbitrary action of its linear dual. So I'm thinking that A is component-wise finite dimensional. And so with some natural compatibilities between A and A star. And so let's decipher what this category is in each of these cases. So let's take first the Lustig version. So in this case, So I'll write the answer for what this category is. This is what you may call it's modulus of the mixed version of the quantum group. Let me call it rep QG mixed. So what are these? So first of all, these are representations of the quantum torus. So there's a vector space graded by weights. They have on them the local nilpotent action of Lustigs and plus on the one hand, but the negative part is different. They have an arbitrary action, but not of Lustigs UQ and minus, but of its linear dual, which is the Katz-de Concini version. So it's, if you wish, it's so UQ and minus Katz-de Concini Lustig version. So it's kind of this lopsided beast. And it hasn't been studied in great detail in the literature, but in fact it's actually important. So if you consider the Katz-de Concini version, so the category that you get, let me call it rep Q G mixed bad, lack of better terminology. So it's the same thing, but you have the plus version of Katz-de Concini acting locally nilpotently, and Lustig version of n minus acting in an arbitrary way. So
Why is it worse than that?
no, I'm not. It's not value judgment. It's just I didn't come up with a. No. So I mean, kind of, if you're interested, I mean, because you're ultimately interested in something kind of, you want to approximate the original quantum group where you have Lustigs and plus acting nilpotently, and Lustigs and minus acting nilpotently, and this approximates that much better than this.
So can I say again, the second thing means what?
So Katz-de Concini plus part acts locally nilpotently, and Lustigs and minus acting in an arbitrary way. I'm sure this is closer to what you want in this. And finally, when A is UQ and plus small, so what you get, let me call it rep QG small, and well, it'll be vector spaces with action of small n plus and action of this its dual, which is exactly the small n minus. So what you get is actually representations of the graded version of the small quantum group. So it's what you can call UQG small modules, just graded version. So this is a category that kind of makes, well, it's more familiar to representation theorists. All right.
By the way, what kind of Q are you considering? Do the quantum Frobenius goes into G or G check?
No, it goes to something. It goes to some H, which can be read off this Q. Sometimes a G, sometimes a G check.
Okay.
So, all right. So
Generic is also found.
no, I'm specific in the roots of unity case.
But is there anything you said which does not apply to generic?
So far, not. Okay, so therefore, all of these categories of interest will be interpreted as modules for this omega. Well, now you can think that this factorization modules is something unwieldy.
Modules are, does mean five-dimensional modules or all modules?
No, I work with large categories.
So just all modules with these conditions.
Yeah.
Like in cases 1 and 2.
Yeah. So now I want to say that, so in fact, this category consists of sheaves on schemes or in schemes. So it's something kind of geometrically very manageable. So let's assume that our A is graded, well, it's an object of rep QT by, let me call lambda pos. So in this case, its causal dual is graded by lambda neg, and so this omega is so if I think of it, so let me think of it as sheaves on Gr T. Factorizable version. So it's supported on the components of the affine Grassmannian that corresponds to negative negative co-weights. So I want to say that when you consider the factorization version, you effectively live on finite dimensional varieties. So specifically, well, a proper way to do it would have been to pass to round space of the curve. But inside here there is the, let me say, the negative part where I allow my co-weights to be only at the negative, belong to the negative cone, and that is a disjoint union of partially symmetrized powers of the curve. So namely, if lambda is written as a sum of negative simple roots, then x to the lambda is just the product of the versus of the Dynkin diagram of symmetric powers of the curve. And effectively, so this your omega A amounts to a collection of twisted sheaves on this disjoint union of x to the lambda. And moreover, the same happens to when you consider modules. So I said that you can go from objects of the infinite center to factorization modules. Let me denote this functor m goes to am. So there will also be sheaves on a slight version of this. Let me call this space configurations. So it will be also sheaves on the space of configurations with one marked point. So the difference is that, so here I allow only negative weights just everywhere, and here the difference is that I'll consider configurations where away from my point x are required to be negative, and they're required to be, and they are allowed to be arbitrary at my point x. So if you wish, this is a scheme and this is an in scheme. All right. Okay, so, well, this was a long detour to kind of factorization interpretations of quantum groups. So now I can refine better the original conjecture. So I will not only say that I have an abstract equivalence, I will say well, how this equivalence behaves with respect to this algebras omega. So specifically, I want to address the following question. So I start with M, which is a representation of Lustig's quantum group as is. And then I can send it to any of my three categories. So
far quantum groups make sense only when Q is in C star, right?
Because we are on the Betty side? Is that the question?
Yeah. So you said that you would define some versions of quantum group in the L-adic sense.
So specifically, what I mean is this. So this algebras omega Q, they make sense in arbitrary sheaf theory. So all these mixed versions, they make sense in arbitrary sheaf theory. So I did not say how this specific one makes sense in arbitrary theory, just believe me that it does. So all the mixed ones do. So you have to do something to express this one as well. Let me just not do it right now. But whatever it is, it does map to all of these mixed versions. Bad and rep QG small. So namely, if you have the action of honest Lustig's quantum group, you can restrict to all of these algebras. So therefore, if you start with an object with a representation of the quantum group, you can attach to it 3 different factorization objects. You can do omega of m Lustig, which will be a factorization module for omega Lustig. You can do omega m Gaitsgory, and you can do omega m small. So all will be sheaves on this configuration space with a marked point, but they'll factorize with respect to the corresponding algebras. And let me tell you what the fibers are, what these guys look like. So fix a point of your configuration space, by which I mean it's a divisor that it's a sum of points, let me call it xi prime, different from a distinguished point x, with some lambda I xi, and lambda I are negative weights, plus lambda x, and x is arbitrary. So let me call it x underlined. This is a point in the configuration space. And so I can take my omega m, and let me take the Schrieg fiber of this omega m at such a point. And let me give a description of what it looks like in terms of the original module for the quantum group. So what it will be a tensor Schrieg fiber, it's kind of cohomology with support. Can also do the fiber. So what it will be this. You're taking x from augmentation to your m. It will be tensor x from augmentation to augmentation. Exactly. Before I say over what, I say which graded component. So here I take lambda, and for each I take lambda I, but x over what depends on which version I take. So let me take x over uq n plus question mark. So if I want Lustig version, I take Lustig version. If I want Gaitsgory version, I Gaitsgory version. If I want the small, I take the small version. So basically, these factorization gadgets encode cohomologies of M with respect to the corresponding version of the quantum group.
Is it important that you started with M was originally an element of G?
As opposed to?
I mean, could you start with some M which was one of these mixed versions?
Yeah. Yes. Yes. Yeah, absolutely. I'm saying that, but if I start with FQG, it lives in all 3 versions. So maybe in the remaining 5 minutes, what I want to do, so what I've constructed is the following. If start with the representation of the quantum group, I construct this factorizable sheaves on the configuration space, factorizable with respect to the corresponding algebras. What I want to do, I want to say what this procedure corresponds on the Whittaker side. And then it looks kind of interesting from the geometric point of view. So, want to describe this procedure on the Whittaker side. All right. So what we'll do is this. We start with object which was on the Whittaker category, let's say a fine Grassmannian at 1 point. And the first thing that we do, well, we consider the factorizable version. You can consider the factorizable version of the Grassmannian, let me say, over the configuration space. You can consider over the entire round space, but in particular restrict to this configuration space. Yeah, it's divisors that are negative away from my point x and arbitrary at my point x. So in this configuration space that lives over, configuration space version of the Grassmannian, it lives over the configuration space itself. Let me call this map pi. So And so this Whittaker procedure, well, I start with the Whittaker sheaf of one point, but then I can insert the vacuum everywhere else. And so this, from this F, I can produce, let me call this spread. Over the entire round space.
There are no way, I mean, it's just, it's a round space. I mean, there are no weights there.
Yes. So configuration space maps to the round space. Just pull back. This, yeah, it sees no weights whatsoever. But what you're saying will appear in just about one second. So far, I started with the Whittaker sheaf at one point, and I spread it over the entire round space by inserting the vacuum, and then I pull back to configuration space. So then I want to do something with it to produce my various versions of the omega. So here's the first thing that I can do. All right. I'm out of, but we started late. I think I have.
We didn't start late. We started.
Okay, so I have 5 more minutes. All right, so now this, okay. So inside here, I have what I can call S minus, and that's where this weights will start to appear. So namely, well, let me say what it is fiber-wise. So if you fix a point on the configuration space which such a divisor, the fiber of the Grassmannian over this point will be just the product of Grassmannians. It'll be just the Grassmannian at the point x times the product of Grassmannians at other points xi. And inside, I consider the corresponding semi-infinite orbits. So inside here, I'll consider, to my co-weights, yes, n minus of k t to the lambda times so this is my semi-infinite orbit. So far, orbits. So let me call it S minus, let me call it pi minus. So here's the first operation that I can do. Well, I start with my F, I created the spread F, and I just pull it back, always with a shriek. Pardon? Ups. Pardon me?
F was Whittaker with respect to n plus.
F with Whittaker with respect to n plus. So I create my spread F, I pull it back to this S minus, and then I star push forward onto the configuration space. And this way I get a sheaf on the configuration space. So if you were paying attention, you would have caught me here, because I'm dealing with twisted sheaves, and I cannot just take the Ram homology of twisted sheaves. So something is going on. So what is going on is that I have here a twisting, and have here a twisting, because configuration space is just a part of the affine Grassmannian for the torus. The claim is that when you restrict these two twistings to S minus, they canonically agree. So therefore, when I pull back my twisted sheaf to here, it does make sense to take it the direct image here. So this is an operation. So I start with F and I create a sheaf in the configuration space. So the claim is that that is supposed to correspond to the kind of the baddest guy of the three. So this is the cut de Concini version. So it is, I said the baddest because, well, eventually we want to prove this theorem, and it's this cut de Concini version, this mixed bad version, it's the farthest approximation to the category representation of the quantum group. So if you were to work with this, you will never get anything. So kind of it's really not suitable to prove something. So what you really want to do, you want to extract Lustigs and the small versions. So so the last thing I'll explain is how to do that. So we're still looking at this picture, and so what you have to do is this. There are the following two additional operations. You can start with the dualizing sheaf on S minus. It's an untwisted sheaf, and consider it's. So let me just slow down and say exactly what I mean. So on this Gaitsgory run, configuration X, consider the twisting, which is the ratio of the two twistings, which is the ratio. There is a twisting that comes from the Grassmannian, and there's the twisting that comes from here, and consider their ratio. So what we know is that if you consider this twisting, it's canonically trivialized over S minus. So therefore, you can start, write it here, with the dualizing sheaf over this S minus and consider it as a sheaf with respect to this ratio twisting, and then you can consider its shriek push forward onto the entire thing, and that'll be as a sheaf with respect to this ratio twisting. Then you can shriek tensor it by the spread of F, and this was twisted with respect to the twisting of the affine Grassmannian, and when you consider the tensor product, the twistings add up, and this is twisted with respect to the pullback of the twisting from the affine from the configuration space. And then you can take a star push forward downstairs. And so the claim is that this guy will correspond to Lustig's. Okay, this is.
Isn't it the same as to put star there instead of shriek?
No. No, because we're dealing with the shriek pullback here.
Yeah, what happens if I put star pullback there?
That makes no sense. So we're dealing with this in Sheaves.
Okay.
So it's only this thing that makes sense. So and the last thing that I'll say is that what you have to do to get the small version, it is the small version that is actually used in the proof. So if you want to get the small version, you have to use here the shriek star. And so this becomes tricky, because what do you mean by shriek star? So this is kind of, I want to use the intersection, some version of intersection cohomology on the closure of S minus orbit. So it's not.
It's supposed to be the only place where we're supposed to use Q0 diffusion, right?
The what?
I mean, that should be the only place where it's supposed to use the Q0 diffusion. Otherwise.
Yes. So if U is not a root of unity, all three versions will coincide.
Yeah, but here there should be something specific which should.
Yes. So and when it's root of unity, well, it always makes sense, but they'll be different if Q is root of unity. So you have to develop the notion of intersection cohomology on the closure of S minus orbit, and this is something that has been done recently. So it's intersection cohomology sheaf in the semi-infinite setting, and if you use that, so then you will get the small version of the quantum group, and this is something that eventually allows you to prove the expected equivalence. All right, so.